Okay, hi everyone. I am Mark Booth. My background is in studying debris disks, primarily through observations with ALMA. And 2 years ago, I joined the AtLAST team and moved here to Edinburgh to work on the science work package, primarily coordinating the science working groups and writing up the kind of overview report of the science. So today I'm going to be focusing on telling you about all the science we intend to do with AtLAST and how that shapes the requirements that Tony has just been telling you about. So as part of this, we formed a number of working groups covering everything from the distant universe to studying our own sun. And from these working groups, we produced 8 case studies. These are all now published. You can go to the Open Research Europe website or find them on ADS or Archive. And there are also summaries of these case studies in the SPIE proceedings and the overview report that I wrote. And so now I'll just give you a very brief overview of all of these. And I think in the future, we'll be having some more in-depth talks in this AtLAST Forum series by some of these authors. So starting off with the very distant universe, by surveying galaxies at high redshift, we can learn a lot about galaxy evolution. And one key thing is really getting down to fainter galaxies. Like at the moment, we only really see the very brightest galaxies in these large area surveys. But with a telescope like this, we can sort of get down to galaxies that are like Milky Way luminosities, looking across cosmic time from going out to at least redshifts of 5, maybe even 8. As an example, here are a couple of example cases from the paper. One is considering a continuum survey of 1,000 degrees squared over 1,000 hours, and that would be able to observe probably about 50 million galaxies in multiple bands, really sort of getting good constraints on star formation rates of these fainter galaxies. And then with spectroscopic surveys, one can conduct a 3,000-hour survey over a degree squared and detect about 100,000 galaxies, getting CO lines to understand how the gas evolves in these systems over time. And through other surveys of distant galaxies, we also expect to be able to place constraints on things like the Hubble parameter, and so helping to potentially resolve this Hubble tension that there is in cosmology at the moment. If we then consider the sort of hot and ionized gas around these galaxies and galaxy clusters, there's this effect called the Sunyaev-Seldovich effect, which involves CMB photons scattering off electrons in the hot plasma. And this is seen at these submillimeter wavelengths and allows us to sort of better understand the sort of dynamics and the kinematics of the gas and how the galaxies kind of interact with the large scale structure of the universe. Then considering more the gas itself, the poles, the cold gas that surrounds the galaxies in this circumgalactic medium. By studying the atomic and molecular lines, we can understand the physical properties of the gas and how this how and the feedback that goes on between the gas in the circumgalactic medium and the interstellar medium, how this impacts star formation. And this is really particularly interesting observing this in submillimeter, because a lot of these lines, these are kind of far infrared lines at their rest velocities, but at these higher redshifts, then they're being redshifted into the submillimeter. So that's why we're really keen to get to the submillimeter for this. Looking at more nearby galaxies, this is where we can to really take advantage of a high field of view telescope to quickly map things like the large and small Magellanic clouds, and also by observing molecular gas in sort of millions of nearby galaxies to really understand how the CO evolves and how star formation, and also by looking at the magnetic field, using polarization to look at the magnetic fields, we can understand how that interacts with the star formation processes. Now, considering our own galaxy, this is the galactic plane itself is, of course, filling our sky, and by looking across the plane, we can understand star formation in our own galaxy, and investigating how the chemistry, the magnetic fields, the dynamics, how this all plays a role in forming the stars, and then following the evolution to planetary systems by looking at the nearby stars, like these debris disks, like this one here is a model of Epsilon Eridani, the closest debris disk to us, and understand that helps us understand the kind of present day environment of these planetary systems. So in order to do that, of course, we really need to understand a vast amount of different scales, from the giant molecular clouds all the way down to kind of the individual star-forming cores, and then the planetary systems themselves that evolve out of this. Now moving to our solar system, we'll be able to use AtLAST to observe all of the planets in our solar system. This can help us to look at the weather and the chemistry and understand seasonal variations by doing regular follow-ups of the planets. And one of the great advantages of having a single dish is always having the same resolution no matter what time of year you're looking, unlike interferometers that are often like changing configurations. In addition to the planets, we'll even be able to study some of the moons of the planets, so looking at things like the icy plumes coming out of these icy moons, and studying the chemistry in those to understand the chemistry in the subsurface oceans. And then also with the comets, we can look at the chemistry in the comets. For instance, understanding the sort of delivery of Earth's water and organics. By studying things like the HDO line, you can see how that relates to Earth's oceans and connect up whether Earth's water has come from comets or from asteroids. Then in the center of the solar system is the sun itself. And one of the great things about observing in the submillimeter is that you can, with just like a few tweaks to the telescope, you can enable observations of the sun. And this is incredibly useful for understanding how the things like, especially the chromosphere, is particularly is kind of when we observe in the submillimeter, we can observing at different bands is telling us about different layers of the chromosphere, so we can understand how that varies across a solar rotation or across a solar activity cycle. And with AtLAST, we'd also be able to be doing some sort of detailed imaging of areas where like flares occur or there are active regions. This helps us understand solar weather, which is becoming increasingly important the more satellites we put up. So it's kind of very directly relevant to society as a whole. Now, with our plans for making this a telescope with a large field of view and a very high sensitivity, this drastically increases our possibilities for detecting transient events. And so this could be a wide range of things. For instance, detecting new asteroids as they kind of fly by the Earth, to studying things like flares coming from protostars, or even active galactic nuclei. And so these observations could either be triggered by other telescopes, for instance, telescopes that sort of detect gamma ray bursts. It could trigger observations of AtLAST, but then also AtLAST could help trigger observations done with other telescopes. So for instance, here I'm showing this plot of the afterglow of a gamma ray burst, and you can see here how it's as observations from such a wide range of frequencies and how useful that is in understanding how the spectrum evolves over time. Finally, there's one project that didn't end up going into a case study, but had already been sort of published before, was how AtLAST can help with millimeter and submillimeter VLBI. So a particularly interesting idea here is like many of you will recognize this image of a black hole taken by the Event Horizon Telescope. And what these teams hope to do in the future is to go to shorter wavelengths where you can get much better resolution and actually resolve the photon rings, because here we just see one ring, but with a higher resolution you will actually be able to distinguish between different photon rings to better understand the physics going on around these supermassive black holes.
You have 5 minutes.
Okay. So yeah, moving on to that, from that, like what does that all mean for the requirements on the telescope itself? So firstly, the reason why we're keen for this to be single dish is so that it complements things like ALMA and NOEMA, where when you observe some of these many sort of large-scale structures in the universe with interferometers, you end up resolving out a lot of the sort of detail. And so by making this a single dish telescope, we can really kind of pick up all of the sort of gas and dust that's there that's just not seen by the interferometers. We're very keen for this to be a large telescope, 50-meter dish, because one of the main reasons for this is getting the resolution that allows us to separate sources and avoid confusion noise. So particularly for things like galaxy surveys, with the resolution we expect, we can resolve 82% of the cosmic infrared background. And even in the solar system, this also allows you to sort of pick out the moons from the planets. And this large collecting area naturally gives you a much higher sensitivity, so thus reducing your observing times. As I was saying, like a lot of the structures I was talking about are very large scale, and so having a large field of view really allows us to sort of quickly map things like the galactic plane, and also provides us with the sensitivity for capturing these kind of degree scale structures, such as those seen by the SZ effect. So we're not like losing any emission. For the wavelength range, we're very keen for this to sort of cover from the submillimeters, so from like 300 microns all up to like 9-10 millimeters. The reasons for this that you can help you distinguish between different effects. For instance, things like here on the top right, I'm showing the thermal and kinetic Sunyaev-Zelderich effects and how the and how different they are across the wavelengths. Thus, you need these sort of different wavelengths to really be able to distinguish between these effects. Similarly, for things like galaxies, you'd be looking at like sort of thermal emission in the submillimeter and then free emission in the millimeter, and you want to distinguish those. And also then for getting a very wide range of chemical elements, such as when we look at comets, I want to see things like the HDO lines. So we're very keen for there to be a number of different instruments on this telescope. One of them would, of course, be a continuum camera, which we'd want to be a large format camera to make full use of the field of view. We also want this to be multi-chroic, so it's picking up different wavelengths simultaneously, and to have polarization capabilities in order to study magnetic fields, and also the capability to do solar observing. Although we might even have a sort of dedicated solar instrument for that. Then with spectral lines, we want to be doing high resolution spectroscopy, so we can get down to resolutions such as like 0.01 kilometer per second in order for sort of galactic plane studies to resolve the sort of double peak structures and investigate the dynamics of the gas in these systems, such as this pre-stellar core. And we also want a very wide bandwidth in order to be able to simultaneously observe many different spectral lines. For the more distant galaxies, where we don't need such a high resolution, but a large field of view is much more important. So you we could envisage such a thing, these integral field units that have a very wide field of view and can pick up thousands of galaxies in one image. And even sort of going beyond the telescope and instruments themselves, we even have a number of requirements on the operations. The wide variety of science cases means we'll be having sort of expecting both small and large observing programs. So there'll be some sort of very large surveys, but also very small programs just to observe individual targets. We're expecting all of these transient science to be opened up, and so that then puts a lot of requirements in terms of things that are sort of time critical, looking at things like targets of opportunity, multi-epoch observations, and coordinating with other observatories. Similarly, in terms of coordination for doing things like the joining part of the Event Horizon Telescope, we obviously need to coordinate strongly. That obviously requires a lot of strong coordination between the different telescopes that are part of that network and some like specialized back-end equipment. So just to wrap up, the key science drivers from all this. Firstly, we're very interested in like where are all the baryons, where's the baryonic matter, so all the understanding where and measuring the total gas and dust content of the Milky Way and distant galaxies and interstellar and circumgalactic medium. Making sure that we're not just focusing on the very brightest things, but really getting down to the typical populations, the galaxies that are as faint as the Milky Way, looking at circumstellar disks that are as faint as the Kuiper belt in our solar system. Then we have how do structures interact with their environments, understanding these interactions between the gas and dust in galaxies, and how supernova effects and star formation come into play with that, as well as magnetic fields and the chemistry. So for that, we need a lot of high spectral resolution line observations and high sensitivity to large and low surface brightness structures. Then finally, what does the time varying submillimeter sky look like? So, we're with this high sensitivity and large field of view, we're really hoping to sort of open up the submillimeter transient observations. And for that, we need a lot of like high cadenced and rapid response observations, and built-in transient detection algorithms, and a high time resolution to really track how variable these sources are. Which is what leads to all these telescope requirements that Tony was describing in the previous talk. And with that, I'll just say, thank you for watching. And if you're interested, I just want to mention to keep track of like what we're doing, go to our website and you can sign up to our newsletter. In the second phase of AtLAST, there's going to be a lot more work on developing a science reference plan, which will be led from Oslo. So I think Claudia can maybe speak to a bit more of that in the discussion session. With that, I'll end.